So actually, just for your own sake, C of P, C of K, if you remember last time. So in other words, if I have D of P, if you have this guy, how to get C of K? How to get our C of K from D of P? How to get that? What to do here to get C of K? Come on. Come on, guys. What is C of K first? What's C of K? Because we need to know. What's C of K? What do you call it?
Still Dalton function?
It's what? I'm sorry?
Still Dalton function.
G-Dawson function, that's right. And what does it represent for your system? What does it represent? Is it your transfer function? Is it your step response? Is it frequency response? Is it impulse response? What does it represent?
Frequency.
Is it the transfer function in the Laplace domain? It's not in the Laplace domain. It's what? C of K is what?
G is frequency.
It's your frequency response. K is omega. K is your omega. K is omega B over U. This is in the frequency domain. It's a complex number in the frequency domain. This is your frequency response. So how to get the frequency response from transfer function? How to do that? How to get frequency response from transfer function? This is what we just reviewed here. I omega. Yeah. So this guy will replace P by I omega, but we are non-dimensional, so we'll put IK. K is our omega. So if we have a transfer function for our unstable aerodynamics, we'll just replace each Laplace, S or P, by IK. I get immediately G-Dawson function, okay? Guys, if you have a question, please don't let it pass. Like I said, I mean, you'll not find places to review these things, so this is your only chance. So if you have a question, just come up with it. Don't let it pass. So C of K last time, luckily, this is what G-Dawson found. H12 plus I H0 2 of K. And luckily, this is a nice function, MATLAB Bessel 1, Bessel H. Actually, it can be written another way. So it can be written in this way. K1 of IK over K1 plus K0. And this guy is modified Bessel function of second kind of order 1. Anyone, it's easy. In MATLAB, it's Bessel K instead of Bessel H. Bessel K and the order and the argument. The argument is IK, right? IK. So if I'm telling you, so K1 and K0 are functions, known functions. You use MATLAB command and you get these functions. If I'm telling you that this is my frequency response, which is the frequency response is the transfer function by replacing P by IK. Can you give me my transfer function immediately, D of P? Can you give me D of P equals what?
K1 upon
K1 of
P.
P.
P upon K1. P. K0.
Yeah, we got our transfer function. Okay? So this is your transfer function, which is not a nice one, we'll talk about that later, but it's your, indeed, it's your potential flow transfer function. Exact. It's exact. Okay?
So I have a question.
Yes.
So why are we converting this K to like a transfer function? Why are we like converting C of K to?
Because it's very hard to deal with. Okay, here is your transfer function. Here is your frequency response. We'll do it now in the very next step. So we'll do the same two responses with D of P, like what we did with the generic transfer function. Here is the step response, and here is your frequency response. So we already said that our frequency response, C of K, is D of P after replacing P by IK or I omega. Okay? We already know our C of k, it looks like this. So frequency domain, the magnitude of C of k starts with unity and saturates at 1/2. The phase of which starts with 0, of course, and then come back. This is k, and this is the phase. Okay? This figure by itself is not very useful in doing simulations. When we do simulation, we like to have a transfer function or a state space model, right? These are very convenient. We have even MATLAB commands that if you have your transfer function, you can give it to it subject to any input you like. But here, given this guy, given any input you like, t squared, well, it's very hard to determine the output due to an angle of attack that is t squared, for example. I mean, we can sit and try to do it, but this was the subject of last time. If it's periodic, we're going to use Fourier series. If it's not periodic, we're going to use Fourier transform. It's not quite convenient. There is huge legacy in dynamics and control that you can exploit if you have a transfer function or a state space model. But more importantly, and we'll come to this in 10 minutes or so. But like I said, frequency response by itself is not very convenient. Actually, when we do things experimentally in dynamics and control, you get the frequency response. The first thing to do is to approximate this frequency response by a transfer function, to get transfer function out of it. It's very convenient to deal with transfer functions. Or state space models, of course. State space model is even more convenient. So we have this guy. This is our frequency response, which is determined by Tudorson, 1935. What is the step response? Anybody remembers what's the step response that is corresponding to Tudorson? What's the step response? What's the step response?
Wagner function?
It's Wagner function. 5s, again, so this is our s, our time. So it's non-dimensional time, tu over b. Okay? And this is Wagner function. The asymptote is unity, and these guys have. And you can apply the concepts that we had from before. So what is your DC gain here? What is your DC gain? 1, right? What is the DC gain? It's here in time. It's the infinite time or zero frequency. Okay? The infinite time or zero frequency. So this is your DC gain. Your infinite time or zero frequency, and this makes very sense. Why? Because the input to our transfer function is the quasi-steady lift, is the steady lift. The output is the unsteady lift. So the DC gain, how much amplification or reduction you will get in the steady state from the steady lift, well, it's unity, of course, right? The DC gain is unity. This makes sense. It's by definition, it's nothing, no more physics. And also, the phase is 0. So yeah, in steady state, frequency is 0, k is frequency. So at 0 frequency, you get the steady state lift 1 times the input. And at no lag, no dynamics. But what's bothering here is the high frequency gain. What's the high frequency gain? What's the high frequency gain? Half. So it is very easy. It's not a rocket science. High frequency gain. So I'm talking about the frequency domain. Here is the frequency domain. High frequency, and this is the gain curve. So it's half. The high frequency gain is half. And how do you get it from there? It's the initial value, right? So you see them matching. So this is my high frequency gain, which is put frequency infinite or times 0. Okay? In the transfer function, put p is infinite. So what does it imply? This is important. What does it imply here that the high frequency gain is half? First of all, what do you know about the relative degree between denominator and numerator? Is the denominator is strictly larger than numerator, or they are equal in degree?
Equal.
They are equal in degree, and the ratio between the coefficients is exactly half. Okay? Which means that, what does it mean if the two degrees are equal? It means that there will be a component of the output that depends on this input at this time instant. It's exactly half of it. So when we apply step input, step change in the angle of attack, we immediately get half of its value, half of the steady state lift. Immediately get half. The issue is we immediately get half here, and this means that if you change the angle of attack of the airfoil very, very fast, infinitely fast, you will get half of the amplitude, right? According to this dorsal model. These findings, not only that, you will get half of its value at zero lag. Zero lag. You will get it immediately with half the amplitude for infinite frequency. This does not really make sense, right? This doesn't make sense.
So is this saying that there's a part of the system that has no dynamics that passes through directly, and another part that has dynamics?
Exactly. So one of the very interesting papers by Peters, 2008. You can see it's recent. I mean, relatively recent. Journal of Fluids and Structures. He showed that. Not exactly, but you can infer from his words and paper the following. The circulatory lift is not solely due to circulation. It's not lifted due to circulation. Okay, because this is very confusing. The circulatory lift is not lifted due to circulation. The way the pioneers, Tudorson, von Karman-Sears, M. Wagner, all the old generation, tend to define the circulatory lift was not the lift due to circulation for some reason which we do not know. But if you follow Peters, you will immediately see that the circulatory lift is, hopefully if we have some time in this course, I will derive this relation to you. We will see. So it's the lift due to circulation plus some acceleration terms. Some non-circulatory like terms. Okay? Which we already discussed that the non-circulatory like terms are instant, right? In response. So the circulatory lift actually has non-circulatory contribution in it. If you look at this guy, the lift due to circulation, in particular at the circulation, the frequency response has a strictly proper transfer function. So this is gamma over gamma quasi-steady. We don't have a name for it. So the transfer function of circulation is not C of K, it's not transfer function of lift, because, like I said, the lift is not the lift due to circulation. The transfer function, of course, it starts from unity here, the DC gain, and it monotonically approaches zero, high frequency gain. And this guy starts here with zero in phase, and this thing is 45 degrees. Can you tell me about the relative degree between denominator and numerator? What's the relative degree?
Denominator is higher.
Higher by how much?
1.
1, this would be 90 degrees. So yeah, it's higher by half. So the high frequency response, the high frequency limit of your transfer function is 1 over square root S, or 1 over square root P. It's a fractional integrator. I'll give it to you here. So the relation actually between gamma over gamma quasi-steady, this is the transfer function that is function of frequency, this is the frequency response. We tend to expect this is C of K. Okay? It's not. So here is the relation that we derived recently. So, it's not a big deal, you can just manipulate things, but it's not explicitly stated in books. I guess this is negative 2 e to the negative ik divided by pi ik h12 of k, and here is c of k. Okay? So the transfer function of frequency is not c of k, it has this guy. This is just to make it clear, this is I. So, remember gamma, here is gamma over left circulatory, which we tend to think that this is unity. It's not. It's gamma over gamma quasi-steady times gamma quasi-steady over left circulatory, right? So, and maybe we'll have rho u somewhere, because this is, you know, so this is left quasi-steady over rho u, anyway, just to make it clear. So gamma over gamma quasi-steady is this guy. Left circulatory divided by left quasi-steady, this is the 1 over c of k, right? So actually the gamma over left circulatory, maybe we have rho u here, just to make it, you know, non-dimensional, is this thing without the c of k, right? Just this thing without the c of k. So this is as a function of k. The transfer function between gamma and circulatory left is negative 2 e negative ik divided by pi I k h12 of k, and this is frequency domain. If I want to get the transfer function, you want to do that. You want to do what? You want to get the transfer function from here. You want to do what? Replace what by what?
Ik.
Ik by p, right? So hopefully everything is written in terms of ik. This is really ik, this is k, so I want to replace this. We will use the relation between Bessel functions, so this is actually negative pi over 2 h1 of k is simply k1 of ik. So now we have a transfer function. Here is the airfoil motion, which is left quasi-steady, c of k or d of p. This is your circulatory lift, right? Then from the circulatory lift to your gamma, this is what we found now. Can you read me this transfer function? It's what? Here is rho u. Is e to the negative p, right? Divided by p k1 of p.